Good morning, everybody. My name is Stefano Marchidis, and I will be chairing what is the first Plasma-PEPSC seminar. So we have the pleasure and the honor to have with us today Professor Martin Schulz, who is going to talk about the state of MPI, Message Passing Interface, current standard and future plans. Professor Schulz is a full professor and chair of computer architecture and parallel system at the Technische Universität of Munich, which he joined in 2017, as well as a member of the board of directors at the Leibniz Supercomputing Center. Prior to that, he held the positions at the Center of Applied Scientific Computing, CASC, at the Lawrence Livermore National Laboratory and Cornell University. He earned his doctorate in computer science in 2001 from Technical University of Munich and a Master of Science Computer Science from UIUC. His research interests include parallel and distributed architecture as an application, performance monitoring, modeling and analysis, memory systems optimization, parallel programming paradigms, tool supports for parallel programming, power-aware parallel computing, and the fault tolerance at application and system level, as well quantum computing and quantum computer architectures and programming, with a special focus on HPC and quantum computing integration. Professor Schulz has published over 250 peer-reviewed papers and currently serves as the chair of the MPI Forum and the standardization body for the message passing interface, one of the dominating standards of performance computing, and the very much topic of we're going to discuss today. So Martin, again, it's really a pleasure to have you here today to talk about the current state and the future of MPI. Please, the room is yours.
All right, thank you very much. Thank you for the introduction, Stefano. Thank you for inviting me to give you an update on the message passing interface. As Stefano said, I'm very much involved in the standardization, and it's always a pleasure to talk about news from MPI. There's been a lot of happening in the last couple of years, and so I want to give an overview of where we are with the current standard or standards, to be more precise. And then I'm going to give a little bit of an outlook at the end of where we're planning on going. I think this all relates very much to what we want to do in this Center of Excellence, things that we can hopefully apply to the code, or also things that we may need for the code. So I'm also looking for feedback here of things that you want to see taken back to the MPI forum to be introduced into the standard, so we have it available for our codes. Also, feel free to jump in. We can make this a little bit more free. There's a lot of individual topics here. If some topic interests you particular, just jump in, don't wait until the end, and we'll adjust the time and the time allocation accordingly. But to start with, where are we? So the biggest release in MPI recently was MPI 4.0, which was now published about 2.5 years ago. We did this in the middle of the Corona time, which was a complete change for how the forum actually worked. The forum used to be in presence only. Of course, now they changed to in virtual only, but now we are in a hybrid scheme. So Corona had a really big impact on us, but that's also why you see the typical ratification picture with these wonderful tiles here. There have been a lot of big additions to MPI 4.0 that can have at least quite an impact on codes. And so we're also curious to hear how this could impact the codes in Plasma-PEPSC. Solution for big count, partition communication, persistent collectives, improved error handling, topology solutions, MPI sessions. There's a whole bunch of that. And I will go through those in a little bit more detail to introduce them, in case you've seen them more. One of the biggest ones is what we lovingly call the embiggerment. The embiggerment comes from the point is that we had the problem that our count arguments in MPI are limited to 32 bits. There were integers, and based on the way the interface was written, just changing this into a long or changing this into a different type was not possible. But on the other hand, so we had more and more applications complaining that this is not big enough for them, particularly also since we use this on the I/O space as well. There was an initial trick introduced in MPI 3 that allowed you to do larger data types. You could construct something larger of data types, but that ended up being, yeah, it worked for point-to-point. It didn't really work for collectives and had other problems as well. So there was the general consensus that we needed something else. The question, how do you do this? So the question is, how do you do this? Just changing the arguments, that doesn't work because that breaks any kind of previous code. We played a lot with polymorphic bindings, which actually worked relatively well in Fortran and worked surprisingly well in C, but C++ was an issue here, so we couldn't make this work because this is actually something where C and C++ don't agree very well. And so the only solution we were left at was basically to duplicate the interface and have one with a short and one with a long count. I know this is not the prettiest solution, but it seems at least the only solution that worked and actually gives us some peace of mind that all code still works. So that's exactly what we did, where we actually went through all the bindings, we fixed a lot of stuff, and we introduced all these _C routines. And if you go now through the standard, you will see this. Perhaps if you look at this, anything since MPI 4.0, you will see, for example, with the receive one, you have the standard binding for receive, and there's now a binding with receive. Actually, probably can make this with a laser pointer here. You have a receive C here, _C for count. And if you look at this closely now, you now have the count argument with the type MPI count, which can now be a longer type. And typically it's to like something like this is a 64-bit, but you still have the old one available as well, so the old codes run. For Fortran, the same thing. We have now a receive and a receive with long. Here, we actually didn't have to change the name because Fortran actually allows polymorphism in a nice way. Here we have the integer type, and you have the integer kind MPI count type. So this can be a larger one for the count part. And here you can actually use the same name. So Fortran is a little bit nicer in this sense. And in C, C++, you would have to use one of these other functions and choose the right one depending on your type. And of course, this had a big impact. So we changed 133 functions. Those are all the functions that had a count argument in there with an integer so far. So all these got duplicated. These are not new functions. They just show up in the standard as these additional bindings in that. But of course, in the implementations, you will have to fix that. And we had to take special care of these functions. Those were the functions with the trick of the data type that we already extended. They were added with an _X. There are now _C functions as well. And the X functions are by now deprecated. So that everything's starting to be consistent again. So if you need larger data types or larger operations with larger counts, look for these _C functions. As a kind of side effect, because I think it's kind of cool, this would have been a terrible.
Martin, sorry we have a question from Urs.
Oh yeah, please go ahead.
Hi, I was just wondering, I mean, this looks good. As a code developer, if we introduce something like this incrementally, does this work if we mix them? If there's parts of the code using the _Cs and parts that are not? I mean, assuming, of course, that the parts that need large integers are using the _C, or is that then mixing up internal state?
No, we didn't put any restrictions in the standard. You can mix them as there's just new functions that have a different type. As long as you make sure that you have the right sizing for your own calls, you should be fine.
All right. Okay. Cool.
Any other questions on this? Sorry, I didn't see their hand in time. So the one thing I wanted to say, that this would have been a pain in the butt to do, but we actually found a way to actually do this in a really cool way. So inside of MPI is written as a LaTeX document. Inside the LaTeX document are now special binding environments which run Python, and these Pythons are now used to generate the bindings. So everything gets described in a Python function. Here's an example for MPI send with the different parameters. During the compilation process, there will actually be Python running, creating the LaTeX based on this Python. And so we can now basically do the big count at the end with just flipping a switch at the end. So now we want everything where there's count, we want the _C functions. This has been vetted by our working groups and had the really nice side effect that we now have much more consistency. We found a lot of bugs in these bindings. So you see some changes in there, some erratas actually that we put in because we found a bug in these things. It's much more consistent now. And you'll see a slightly different rendering sometimes. So in case you're wondering why, this is the reason why. The side effect now is also that we can now automate a lot more. And so in the future, you'll actually see a standardized API that allows you to query which functions are in MPI, that allows you to create tools automatically, that allows you to extract the interface. You can do verification tools out of this one, directly driven from the standard from the original document. So I thought it was kind of a nice side effect of doing this big work with the abigament. Any questions on that? Okay, then to the next big thing, partition communication, another big item that was introduced in MPI 4. So the idea is to provide more concurrency in the communication. The idea is you have a point-to-point operation. We make this a persistent point-to-point operation for now, which means you set up this channel, and then you can start the communication over and over again. But instead of having just one buffer to ship, you actually put this buffer into partitions, and you can mark each partition as it's ready, and an MPI can decide to send whenever it wants to send that particular partition, and the same thing on the arriving side as well. So instead of doing something like this, where you have to work on a large message buffer, do a send, and then you have a large receive, you could end up with something like this, where you mark each individual buffer as ready. You basically say this buffer, an MPI can at this point, doesn't have to, but can at this point move the buffer over. Also, the number of partitions on the send and receive side don't have to be the same, so you have some flexibility there as well. And so you can actually go do something like this, where you, in the beginning, say the middle one is ready, and then the middle one gets shipped, and then is shipped. Then you can say the next one is ready, this one gets shipped. Then you say the first one is ready, the first one. So you don't have to stay in order. That partitioning can be basically put out in any kind of order. Whenever you're done with this particular partition, you mark it as ready and leave MPI the decision to ship it over there. And then the notifications, both on the send side and on the receive side, are extremely lightweight. Ideally, they're just really setting a flag or reading a flag, setting a flag that a partition is ready, reading a flag to basically say something can be received, is ready to be received, has been received on the node. And so you can implement them in a very light way, potentially even lightweight environments, and I come back to this in a little bit. It may not need the entire MPI stack, and that opens up the opportunities to do a lot of different options here with the partition communication. Sometimes you may need additional synchronization to make sure it's actually not safe, but give the MPI an opportunity to know that the message can be communicated to the other side, for example, with RDMA. We're adding additional functionality right now to allow you to do this, again, in a very lightweight way. And with that, we've hopefully find a way to communicate these small partitions in a very easy and very fast way. So you may ask yourself, now, why is this so important? When would you have a code that does something like that? Well, the core idea behind that is better support for threads. And so the idea is something like this here, where you have a kernel, as if an iterative application with a for loop, you have a kernel that has an OpenMP piece in here. And this piece works on different data objects. So each thread gets a chunk of the data to compute. And if you want this chunk to be sent to the other side now, you can now create a partition communication. You can start this communication before you head into the parallel region. Here you still have a fully heavyweight MPI. And at the end, you wait. And the wait now doesn't mean wait for the entire operation. It actually waits that every single piece has been sent, but not necessarily in that order or not necessarily at that time. What you can now do here is you do the triggering in here. So the kernel can now be, say, I'm computing my partition, and then I just trigger my MPI ready. This means each thread can now trigger the communication of its own partition without having to wait for the other threads to be ready, without synchronizing with them. MPI just noticed that now and then as these partitions get filled up and get marked, it can send them all at the end, or it can send them piece by piece. But we don't need a heavyweight MPI operation here because we're just marking them as ready. And so we're allowing basically concurrent communication from multiple threads with that. And with that, we have potential of doing more throughput. Of course, it requires a high quality MPI implementation to actually send these things out of a thread environment. But from the API point of view, we're there. And so we can do the heavyweight MPI outside the parallel region, inside only the lightweight triggering. Thread safety is potentially extremely easy to do with that. For threads, we can partition by the threads, and each thread just says, I'm ready, ship my part basically out of that. And then MPI is left with the option to optimize the latency. So that's already in there now, so you can use this now. Again, it's a question how well this is implemented, how well it's optimized, but I know the implementers are working on that to improve the performance of that. So that's a very nice way if you have these threaded environments. Any questions on that piece? The other thing that was introduced in MPI4 are persistent collectives, and they're exactly what you imagine them. Collectives in MPI1 were just blocking. We added non-blocking collectives in MPI3, and now is the third part of that is persistence collectives. The idea is you can set up your collective one time and say, I'm going to do this collective over and over again with the same parameters. and then you can just say kick it off, start, and basically it's the same thing you do with point-to-point persistent operations. And this way, MPI has a chance to optimize for that. I know this was never really fully realized for the point-to-point because there isn't that much to optimize actually. But for collectives, there's potentially a lot to optimize. You can do your whole scheduling. You can have topologies built up in the background. You can map it to topologies. So there's potentially a lot of stuff that can be optimized and that you could realize that. Of course, like with the persistence point-to-point, is the idea that specific send and receives that you use to build that collective never change. So you basically fix all that part. And once you fix that, then MPI can actually take that and optimize whatever it needs to do to get a faster collective going. But by doing this one time and doing this ahead of time, potentially outside of the critical region, you can actually amortize that cost later on and hopefully get better performance. You can do a resource allocation. You can actually reserve stuff on network resources, for example, to do that. And you can also allocate special limited hardware if it's available, and basically prepare your network for doing that. And when you actually run the collective, you can just kick this off. How is this implemented? Basically the same where we did non-blocking collective operations. So there's a one-to-one match between non-blocking calls and persistent calls. Same way where there's a one-to-one match between point-to-point, non-blocking point-to-point, and persistent point-to-point. So for each non-blocking MPI collective, there's also now a persistent variant. Instead of the I collective name, we now have MPI collective init, which sets up this collectives. You get a request object back. You put the same parameters in. You add an additional info parameter just to be nice and have options for the future. And you fix all the rest of the arguments. Then you get the request object back, and then you just start this request object. When you start that turns from an inactive to an active request. The collective gets executed in the background. You wait for that as you do with a persistent point-to-point. When the collective is complete, the wait completes. The request doesn't go away in this case, like with the non-blocking ones. In this case, it just becomes inactive, and you can restart this again as in the next step. The big difference, though, to point-to-point calls, and I want to point this out, is that you cannot match this with other collective calls. So either all processes have to use persistent collectives for a particular operation, or it has to be basically a non-blocking collective or a blocking collective for the other parts. Of course, you can mix, again, blocking persistent and non-persistent operations as long as they're separate operations. But for one operation, they have to match simply because there's so much mechanism behind it, and the semantics is slightly different, so it wouldn't work out this way. But this one gives you the whole benefit then, of course, if you do it this way. And code-wise, this looks like this. So if you have an iterative application where you have an IB cast and I reduce in there, and at the end, you would wait for both of them to be finished. You do this over and over again. So you know now you do the IB cast and the I reduce multiple times. You can now pull these out. You can say, I do a B cast in it with my parameters, I get a request back. I do a reduce in it, I get a request back. And then where you had the IB cast, you do the start for this request, and where you had the I reduce, you would do a start for the second request, which was defined here, and you still wait for all of them. And then you iterate over through that. And the idea is that at this point up here, MPI would already optimize your two collectives, and here you would just use the optimized schedule, and with that get a performance improvement compared to the top. Any questions on this one?
Yeah, Martin, I have a question. Does this persistent collecting also include kind of auto-tuning or optimizing the collective itself? So this looks very similar, for instance, to FFTW when you do a plan at the beginning. And so you pay a cost. And so my question was, is about possibility of having auto-tuning step here.
It could be. There's nothing in the standard that requires that. There's nothing in the standard that prohibits that. But the API is certainly set up in a way that this could be done. So you could have a measurement basically during the init phase and then set up a topology based on that. These inits are actually collective in the sense that everybody has to participate at the same time. So there can be coordination at that time. And so you can do something like a tuning step as well as you want to. these down here don't have to be collective anymore. So at least they're not blocking at this point anymore. So they're kind of loosely synchronized at that point. The order requirements are relaxed a bit because we know what fits together. But up here, you could certainly do that. Whether it's done or not is up to the MPI implementation.
And there is a question from Marcus. Marcus?
Yeah, thank you. Quick question, Martin. Are you aware of MPI implementations already making good use of these options here?
To be honest, for this particular one, I haven't followed them. I would imagine most of them implemented on top of the non-blocking collectives, the regular non-blocking collectives. I don't think there's been that much optimization going in because it's still relatively new. But I could find out and get back to you.
Thank you.
And let's go to the next topic, better error handling. That's also something that got really improved with MPI 4. As you're all very much aware of, if you get an error in MPI, typically your whole MPI application dies, and you have to restart from scratch, and there's very little you can do. Of course, there's a lot of discussion about fault tolerance in MPI, and how can we make this work. A lot of stuff failed. I get back to this towards the end of the talk if we get to that. But there was still the idea, can we get a little bit better than what we are as a first step towards better fault tolerance? So this is not about fault tolerance, it's just about getting a little bit better in it, basically. And so there's been a lot of work in getting the ability to pinpoint errors to particular operations, to enable MPI to cleanly continue if it can, to contain errors to certain communicators, to only raise errors on the communicators that are affected, to have new error handlers which allow you to continue and things like this. There's been a lot of small tweaks in there. So if you're interested in setting up a kind of slightly fault tolerant or towards fault tolerant application, there's some mechanisms now in place. So for example, localized errors for memory allocation. So if a memory allocation fails, there's no need to bring your whole application down. Now the error just comes on self, and if you set to continue, you can fix potentially the memory allocation or change something in your code, or exclude yourself from certain operations or things like that, but you don't have to kill all the other nodes that you have potentially in there. And so there's some mechanisms in there. I don't want to go too much into detail here because it will take us too far, but just for you to have as a background. And what you can do with this now is basically you could do something similar what you can do with sockets on a point-to-point basis. So if you have like a master worker paradigm, you could actually write a fault tolerance application with MPI by handling these point-to-point calls. Collectives are a different issue. They are more tricky. They're not included in this here, but simple things like this could actually do that. And that was done because we had some enterprise application that actually were interested in supporting this. And wanted support for that, and that's why we include that. But we see it also as a first step to go towards a real fault tolerance and also to support some of the fault tolerance proposal as kind of the baselines that they need. But yeah, keep in mind, this is not a fully fault tolerant MPI. At some point, we'll get there, hopefully with MPI 5. Okay, the other thing that was added are topology solutions. We all know hardware is getting more complex, and it's kind of difficult to find out what's going underneath. I mean, there are tools like HWlog, which give you kind of the static distribution, but that's again a different library, and what would you use that? And so MPI actually added ways to basically query what's going on in the system, so you can now adjust your MPI application to that. That's probably internally based on something like HWlog, where MPI can query the information. They can also use other stuff in there. But this gives you now a way to communicate this to the application. And basically, it's this idea, we have hierarchical systems. Basically, so both on the node, but also you look at the whole systems, and we need to know where these things are, and basically need the ability to create a topology-aware communicators. And there's now two types you can do that. One is called the guided mode. There's a particular MPI com split type. That's the new function called MPI com split type. So it's basically the split. You know, MPI, the part of MPI, you can split a communicator based on a color and a key, and with that create subgroups. And here you don't add a color, but you add a type. There's another flag that's being added, and you say, I want this based on the guided mode. You pass an info key, and you say which level you want to say. I want all processes that run on the same node, all processes that run on the same NUMA node, all processes that run in this rack. Of course, these naming schemes are application or system specific. And so there's no guidance on that, on what is supposed to be named. You can find now have a way to query what's there. You have to know your system. But then once you know that name, you can actually figure out how to split your communicator based on that. We didn't want to specify what a rack, what a node, what a NUMA node is, because it's so different between systems. So there's no consensus on that. But once you know it from your system, you can actually use that. And this obviously has the drawback of not knowing what it is. There's a second mode called the unguided mode, where MPI builds this hierarchy in the system. It can have some flexibility to do that. And you basically can just explore this hierarchy then. You start with ComWorld with all processes in your job and say, split it at the next level down. Then you get n new communicators back. You can split them again in the next level down. And so you can go down the tree until you hit a leaf. And the leaf is an individual MPI process running on a particular resource. And with that, you can build the tree. The idea is things that are close in the tree are also close in physical reality, and hence the communication is pretty efficient between the two of them. And if you then use this, you can build up a larger structure. And this would look something like this. If you have this hierarchical structure, you find out where you are in ComWorld. Then you can split the ComWorld with the split type. Use the type ComType hardware unguided, because it's the unguided operation. You create a set of communicators out of this. In this case, you get 2 communicators out of that. They have, of course, now different meanings on the different processes where you called them. You can, again, take this. You can do another unguide. You can split this, and you can see you find now here. You go down in this case to the individual core packages here, and so you can basically MPI can pick what's useful for the system and give you at least a hierarchy, and then you can query, of course, what the hierarchy mean. But again, that may be system specific, so you'll always have to know something about a system. But at least you can get the tree-based hierarchy in a very easy way to work with. Any questions on that? Okay, so hopefully this could be useful to kind of adapt a lot of our applications also to the modern hardware. And then one of the last things I wanted to mention is the MPI sessions. Hopefully, I imagine some of you have heard of this already. It's a completely new way to initialize MPI, to handle initialization, boot up, startup, and also hardware management and resource management. And this comes from a discussion we had several years ago on the MPI forum, where we tried to take a step back and looked at MPI, what's wrong with MPI, what is problematic in this current world that potentially the designers of MPI 25, 30 years ago didn't have on their mind. And so what we came up with, basically, that MPI ComWorld is a very static resource. You get it in the beginning, it never changes. Also, the general communicators are mutable, and that's kind of a good thing because we can rely on that. But on the other hand, it makes it very hard to adapt and to adjust in with a more flexible, dynamic way we have in that. Once you're within an MPI job, there's no way to isolate resources, which makes the fault model a problem, because once a fault happens, containing that fault is really, really difficult. That's also why MPI had that model of aborting everything, basically. There's no way to talk to the runtime system to get information about the system. Also, that was actually done very deliberately in the beginning to reduce complexity, but with the modern systems, it's starting to be more and more necessary to understand what's in the system, how the system is laid out. So again, 25, 30 years ago, that was not the key. We didn't need that. We wanted not to have that. But now with the modern system, it becomes more and more important. And then also, we were seen as kind of a static thing where we don't support new communities. We only support the HPC community. Very little address to applications have different types of needs. We talked already about the socket application before. So how can we support these ways? And so all these things were done for a purpose when they were introduced, because the first one minimized complexity, being immutable, avoided many issues, and made it basically not PVM back then, for those of you who have been around in the PVM time. The isolation wasn't really necessary in the past. There was very little to isolate. These things were, you had one core and one processor on one node. What do you want to isolate there? Right now, of course, this change is quite different. Also, this one was an explicit choice, as I already said. And then MPI was initially targeted for HPC, and is still the main area, and so that was not beginning. So none of these choices that they made 25, 30 years ago was bad. It was correct out of the view from back then, but we needed to look at this now again. And that's actually now exactly the point where we started with the sessions is how can we overcome these issues without really changing what MPI is? We still like MPI. It's still there for a purpose. There's a lot of things that would be done right. We didn't want to compromise that, but we wanted to kind of find a way to also support these new areas in that. So you want to be backwards compatible, same look and feel, and also enable the existing code. We didn't want existing code to go bad. It still was able to run the way it used to be run. And that's kind of why we came up with the MPI sessions, where we're starting to replace MPI init. The single initialization is a general problem, and where we replaced MPI com-world, that static communicator in the beginning. And this is currently an optional thing on the side. There's 2 worlds in there. You can use either way. So it's definitely backwards compatible. What we do long-term is a different story, but for now, these 2 things live next to each other. And so MPI sessions allows you to access the library, first of all, directly on the local process, getting a handle. It's a local operation. Now you can query the runtime system. So now you suddenly have an interaction with the runtime system. You can ask what sets of processes are there, what sets of resources are there. You can get a string back. You can query the string. You can investigate the string. Now you can create a group from that. This is the first step where we actually enter into MPI land. We're creating a group, but a group is still a local object. So we still haven't communicated yet. And then we can slice and dice the group, and now we can create a communicator from that group. And the advantage is now, if you follow this through, by getting a set of process and picking one, by getting a group from that and slicing and dicing that, I never have to create a communicator that spans everything. I will have a set of process that's the world set, so I can create, so it's comparable to MPI com world, but I don't have to. So now I can start wiring up exactly the resources that I need, get communicators for exactly what I need and not more. This increases scalability, reduces overhead, makes things more mutable and more flexible because I can have multiple of these sessions next to each other. I can have multiple of these communicators next to each other. And with that, gain that flexibility that I want with that. And so now we can deliver runtime information, basically by kind of having this exchange with the library. We can also get some kind of resource isolation because the 2 sessions are technically separate. And we create separate groups and separate communicators from that. They're not allowed to interact. The standard explicitly prohibits that. So you have an isolation with that. And we don't have to have that static resource com-world anymore if we don't want to. So this gives us exactly the flexibility what we're looking for. And it's basically just a starting point, right? This is a mechanism to allow us to do that. Using session for its own won't buy you anything in the code, but now we can build on that. And you'll see in the future ideas that we actually start building on that, and we'll use this more and more. And at some point, I think it will become the dominant way of interacting with MPI. And potentially at some point will eliminate the standard MPI init and MPI com world step by step. So that was MPI 4.0. So there was a lot of different functionality. We actually since then published a new MPI. I don't know if everybody has seen this already. We published MPI 4.1 in the beginning of November, just in time for the supercomputing conference. We're now in a hybrid mode. So we're meeting twice a year in a hybrid fashion and twice a year in a virtual fashion. The ratification ended up being a virtual meeting again, so you again see just pretty tiles instead of a pretty group photo. 4.1 obviously was just a small addition. This is an intermediate standard. We did a lot of cleanup. We had to cut some adjustments of terminology because we had so many new concepts introduced. And the 2 big things that were introduced was better support for bsend and a better support for GPU memories. So it's like a minor update, clarifications in there. If you're interested in that, look at this changelog, couple errata items. If you lose one of these 2 functions, please take a look at that. And we also started deprecating functions like these type X shortcuts that we did for the large data types, MPI host that us would be shocked if anybody uses. And probably most importantly, we're deprecating MPI f.h. There should be a one-to-one replacement by using the MPI F08 module. There should not be a problem for any code, but we wanted to get rid of that because that causes more and more problems for the bindings and for that. Note, these are deprecated. They're not removed. They may be removed in a later version, but we encourage you not to use these features anymore. And if you have them in a code, to start taking them out, because at some point they may no longer be supported. At point of new functionalities, there's now functions to get and set status fields in the status object that's necessary for some special use cases. I'm going to skip this for one now. You can now MPI get request. We always had MPI get request get status. So now there's an MPI get status any, all, and some. So you can now figure out what the status is of not just a single request, but a group of requests, similar to what you have with test and wait. The hardware topologies got a little bit further extended by having additional functionality in that. And also, if you ever played with error codes and error classes, you can now not just add them, but you can also remove them now. So a kind of small functionality added on that. So one of the bigger things was the bsend. If you ever use bsend, you can do a bsend, which means it's a buffered send, which MPI will copy the message into a buffer and then send it, which means the bsend returns immediately. You can continue your work. The data is lying in a buffer. You're responsible for providing a buffer with the buffer attach and detach commands. And when we looked at this, we noticed that this is actually not really safe the way it's done. Excuse me, it breaks on communicators and it breaks on sessions in particular. So there's new functionality to get a buffer attached to a particular communicator in a particular session. You can detach it then. And on top of that, sometimes you just want that copy functionality and that you don't want to deal with all the buffer stuff and so on. So there is now an ability to also do an unlimited buffering, as you just say, I don't care about buffers. You deal with the buffers. You allocate them when they're necessary, and you delete them when they're not necessary anymore. Probably takes some more memory, takes some more resources, but makes programming much easier. And you have the choice what to do. So you can choose which mode you want. You can actually choose for each communicator in each session which option you want. And then there's also the ability to wait for that basically until the buffer is flushed. You can also make sure that things get sent out of the buffer when you need to. So also that's a new feature in MPI 4.1. And then the other big feature, and that's maybe perhaps the most interesting one for this group, we added allocator kind infos, which means we can now have the ability to distinguish where memory is living, which memory we're using, whether that's accelerator memory, MPI memory, pinned memory, or just regular system memory. And with that kind of query whether an MPI supports particular, for example, CUDA support, or ROCm support, or level 0 support. And so we can now basically ask MPI, what memories do you support? What do I want? There's a negotiation between the MPI and the application. And based on that, you can choose an optimized path or a slow path. There's a question. David, you had a question? Was it for this?
Yes, Martin, thank you very much. I have a question about bsend.
Yeah.
Does it mean that you also receive or just how it's, because as I understand now, it does not send directly to, to some core, but it puts in the buffer. Then probably this core, which is destination, should know that it has to take from buffer, or how it's handled. And what is the speed? If you compare speed of these operations, so send, receive, and bsend, receive, if you somehow say how optimal it is.
Sure. So there's actually no receive. The bsend only lives on the send side. You basically do a send to a particular MPI rank on a communicator, and this gets copied into the buffer. This is just a local thing. And then after that, MPI will send this the way it would do an MPI send. So the receive on the other side is exactly the same. There's touching that. In point of performance, it is more expensive because you copy the message, or it can be more expensive. MPI could also decide to buffer without it as well, but you guaranteed the buffering is happening. And with that, the semantics of the bsend is different because it's guaranteed to return immediately. It doesn't wait for a receive on the other side to be there, whereas a send could potentially block until the receive. That's the difference.
So it can be really fast because it does not need confirmation. Okay, thank you.
That's right, but also you need memory resources, and if they're not there, then you may run into trouble, right? So if you just have large messages sent with bsend, then you may run out of memory, potentially.
Thank you. Thank you.
Sure. Okay, so the allocator kind of info back to that, so that you can now communicate with the MPI library and ask basically for particular memory operations. And there's different type of, this all works with info keys. We can request certain, you can assert certain memory that you need certain memories, and you can also find out what the library actually supports. And and the trick now is this one is really hard to introduce. We added a trick to do this on ComWorld, but it's so much nicer to do in sessions because now you can attach these requests to when you create a session because there's an info object. So this is the first case where the session really helps us because we now have this new mechanism to initialize. We can negotiate at that level, and you can also have different sessions with different requirements on the memory kinds, so you can really work through with that. And here's an example of how this works. So you basically create a session here. You have an info object where you basically say the things that you would like to see. Then you create the session, you get the info object back, you ask for all the kinds that are supported, and then you look through this list. And if you see now that what you requested is actually there, in this case, we're looking for a CUDA device. Now you know the MPI that you have is CUDA enabled, and you can use a fast path. You can actually send directly from CUDA memory. If it doesn't do that, you may have to choose a slow path where you use regular memories and copy things around additional times. But by figuring this out, you can now add a fast path to the memory. Again, that's a first step to be introduced. There will be much more coming in the upcoming MPIs in that direction. But it's a first way to kind of negotiate with MPI which memories are supported and then basically use them on a fast path. So if you're interested in that in more details, let me know. I have a couple more examples that I can't show today, but I'm happy to send you this or point you to those. So Jim Dynan from NVIDIA, who's driving that working group, has done extensive sets of experiments, extensive examples, and there's also a new site document coming out on this topic. Okay, any questions to that? So where are we on time? We have 10 minutes, okay. So this gives us MPI 4.0, 4.1. This is where we stand right now, so this is brand new. We're already working on MPI 4.2, which is planned as soon as possible because we don't want to make any big changes here. The only thing we would like to introduce in MPI 4.2 is an ABI, so an application binary interface, so that any MPI library can fit to any compiled MPI code. This is currently not the case. If you have a new MPI library, you need to recompile your code. For typical HPC codes, typically not a big deal. But once we start adding containers and industrial applications, that really becomes a nightmare if you do that. And so we'll introduce an ABI that will be optional at first. But if an MPI actually supports that, you can take now an application running inside a container, and you can match it with any ABI-compatible MPI library on the bottom, and you can switch these in and out. You can imagine there's a lot of discussions in there. What is the right interface? How should we do this? We have the two major competing MPIs, MPIG and OpenMPI. They have different ABIs, so they're picking the best from both worlds and writing up a common layer that can be easily translated to the individual pieces, but we'll have that hopefully with MPI 4.2 relatively soon, and then we can at least work with that. We're not planning any other new functionality because the ABI is such an invasive thing that we want to get this done so we can then afterwards cleanly add new things. And that brings me to MPI 5.0. And I don't know how much time we have to run through this, but there's been a lot of new things under discussion. So this is discussion that's going on right now. Of course, we're building on these concepts in MPI 4.0 and 4.1. Partition communication will certainly be increased. We're going to use more and more sessions. The memory kinds is also just a starting point. The idea of persistency will be probably spread more through the standards. You will have more operations where there's also a persistent variant for that. In case you want to repeat things over and over, you want to set up your own schedules. So to expect that. If there's particular interest in pushing any of those, let me know, and I will certainly get in contact with the respective working groups in the MPI forum. And then, of course, there's other features in the discussion. One of the high-up features, of course, is the better support for accelerated architectures that comes out of the direction partition and memory kinds already. You've seen already this goes in this direction. In particular, the partition communication has some really good potential. So I've showed this example before where you basically have no threaded kernel, where you have your partitions and can be able to send them out. This is very nice to work for threads. but you can also extend this to accelerators really nicely, because now you have the heavyweight host environment and you have the lightweight GPU or accelerator environment where you typically don't have an operating system. So you can think something like this, where you, instead of having an OpenP4, you now have a target. You shipping is over to a GPU. You're handing over the request that needs to get somehow translated into a GPU version of the request. And then you can actually run the ready, since it's just setting a flag, on the GPU side. So each GPU can just do the partitions and just say, I'm ready. And then if you even have an MPI and GPU-enabled MPI, it could at this point take it directly from GPU memory and ship it. Right? And so you're bringing GPU and CPUs much closer together without having to run full MPI on the GPU support. So that's something planned and we'll hopefully see relatively soon in experiments. But of course, you can imagine this is not the easiest thing to do, because we then need, of course, bindings for GPUs in MPI, because you need something like the P-Ready needs to be run on the device, and there needs to be a different API for that, or a language extension for that. And you can imagine that's going to give us a whole other can of worms. So thinking like in this case, P-Send, P-Receive, wait starts, all the heavyweight stuff would keep on the host, but something like the P-Ready or the P-Arrive, which is the query call for the receiving partitions, will have to run on the device. And so we are working on that and seeing if we can make this possible. We're also working on better integration with task-based runtime systems. This may also be of interest for some of you. The idea is, can we combine thread continuations with what's happening in MPI? So trigger OpenMP from MPI and trigger MPI from OpenMP to couple these two systems together without having to couple them directly into the standard, which will be a little bit more difficult to do. And so this is one proposal that's currently out there. This may not be the one that gets in, but something like this is being discussed. We create a continuation. Once you are in an OpenMP task, you can now do an iReceive. You can bind this iReceive to a continuation, and with that, finish the task. Once this is done, it would actually call an event. In this event, you can then say, I'm fulfilling an OpenMP event. So this is the MPI part, and callback that can call an OpenMP event. And with that, you can then trigger another task. And so you now have the ability to basically start a communication, one OpenMP task, release that task, wait for it to come back, trigger the new task in the next step. And with that, have that combination of MPI communication and OpenMP tasks. There's actually two competing proposals, one done by the group in Aachen, one done by the group at UTK. They've both been presented. They're both being considered for standardization right now. We'll see which one will work, but they both have the same idea of having these continuations in the MPI standard, and with that, having the better coupling in that. There's a better integration with task runtimes. And I'm going to skip a little bit something here. There's a better tool support. We're going to see a new tool interface, most likely, that replaces PMPI. And then the last thing also, we're going to support more malleabilities. We're going to take the MPI sessions and basically ability to kind of change the process sets on the fly, and with that grow and shrink process sets, and that can then work into growing and shrinking communicators. Now, if we don't have an MPI world anymore, and so we can actually create a new system that replaces world, and that can be smaller and bigger. And with that, we can get real malleability support. That's an ongoing discussion. And then the final thing, what I just want to mention, we're also working on fault tolerance. And there we actually have multiple proposals still in there. We did this for a long time. I know we've been trying over and over again, but some were seen as too heavy, some seen as too oriented to a single model. And so we're trying to find the right balance. There's still a lot of interest in that. We had the first step of the better error handling in MPI 4.0, and now we're actually working on getting the building blocks together that can then really be pieced together. And there's several ideas right now. There's a fine-grained one, which works really on individual processes. That's the ULFM proposal from Tennessee. There's a coarse-grained one, which basically just supports efficient checkpoint restart. That's out of Livermore. And then the third one sits kind of in between and does on a session basis, where you basically blow away sessions, but the rest of the universe lives. So this is kind of a medium grain model. Which one of those will work? If all of them will come in or some of them, we'll have to see, but that's kind of the state of that in Fortran. And if there's interest in that, I'm happy to talk more about this at some other point. So, but basically to say, we have a lot of new features in MPI 4.0 that will hopefully be useful for the applications that we have here. We have MPI 4.1. If you haven't seen this, just take a look at that with some cleanup and some minor features. But this is the current standard here, which has, I think it's much better readable than the 4.0 when we did a lot of work on the text itself. And basically we are pushing for an MPI 4.2 with ABI. There's a lot of research topics in there that we're still working on, particularly for accelerated system, for tooling, for malleability. So expect a lot in the MPI 5.0 time with that. And of course, that means if you're interested in that, you want to push for a certain feature, now is a really good time to participate. We are a very open forum. Any organization can join. Joining just means showing up at the meeting and participating. And with that, you get eligible to vote. And then we hopefully can introduce benefits that help us all. And for this particular project, either feel free to join yourself or run it through me, and I'm happy to be the conduit into the forum for the particular set of codes that we have here. Quick acknowledgement, of course, this is work done by the forum, not by me, what I presented here. And the local stuff is work by my group here in Munich. A lot of them are involved in MPI for obvious reasons. And so there's a lot of work happening here as well. And with that said, if you have any questions, if you want to participate, just shoot me an email. Happy to hook you up. Happy also to take questions and take things back to the forum for the group. Thanks for your attention.